simulation with the tensor code, but first, what I would like to do with the tensor code, and I will present two possibilities of simulation with tensor code. The first possibility is linked to my work I did for my PhD, and the second one is linked to the work I am doing for the postdoc. I am in postdoc at the University St. Mary's in Nova Scotia at Halifax since 1 year and a half. Okay. And so these two possibilities are linked to the fact that I would like to study the turbulent transport, the vertical turbulent transport of chemical species up to the surface of the stars, and I restrict for this talk to main sequence stars and to late to early type. So the work I did for my PhD thesis, I call this work a local study because I use the plane approximation. I can use it, and so I am able to do 2D simulations. And about the work related to my postdoc, I call this work a global study because I do a simulation, 2D simulation of axisymmetric star. So I speak about motion on the size of the star, and I am interested to study the nonlinear evolution of this motion, and if, for example, shearing layers will appear and develop some shearing turbulence, and to see if the shearing turbulence could have an effect on the vertical transport of chemical species to the surface. The first one is more devoted to solar flare stars, the second one to intermediate mass stars. Why intermediate mass stars or more massive stars? It is because we observe lots of abundances, anomalies at the surface of the star. Okay, so just, I don't want, so the talk is quite long, but I won't explain all the information on the slides. Just to try to be not too long. To remember, when we study the turbulent transport is related to the evolution of the stars. So in my case on the main sequence, but it could be on the entire Archer diagram. What I call the standard model, initially it's a model which was unified in the early 90s. It's a 1D model with no rotation and magnetic field. And initially it was assumed the transport in the right zone. So you have two zones, a chaotic one and a relative one. And the position of these two zones in the star depending on the position of the stars, if it is more early or more late. And in the convection zone, just you had inefficient overall mixing described by the mixing theory. So, lastly, in spite of the great success of the standard model, we understood that from observations that we were not able to reproduce, to predict or to reproduce some abundances anomalies at the surface of the sun. For example, it's under abundance for light elements, and for more heavier elements, it was overabundance or other abundance or more heavy elements. And so people, so coming from different groups, proposed to add diffusion processes and meridian circulation in the radiative zones. And to summarize, you have two kinds of diffusion. You have the microscopic one, related to atomic thermal diffusion, gravitational setting coupled with relative pressure, and the macroscopic one, which is in my concern, which is related to turbulent transport, and it is mainly involved by the differential rotation, which must create shearing layers, and the development of the instability of Kelvin-Helmholtz, and in the best case, the development of strong turbulence, which could be a little bit anisotropic or isotropic, but more devoted to small scales, and the meridional circulation, which is a large-scale motion, and which must produce more large-scale turbulence. So if we see the spectrum, so meridional circulation must contribute to the upper part of the turbulent spectrum, and the differential rotation more lower part, close to the distribution range. So if we limit to the non-viscous part of the spectrum. So here you have the same, because my work during my PhD was really related to the dichotomy, so this intermediate zone between the radiative and the corrective one, where seismology showed that from the rotation, the angular rotation the rotation profile, that we might have some shearing. So shearing appearing so in the azimuthal direction, and this shearing could be responsible of some trapping of light element, which could be burned if it is more deeper, but in this area the temperature, for example, of burning of lithium is not enough high. So some people like Michaud of University of Montreal have suggested, and some people of Toulouse have suggested that it could be trapped in this area thanks to strong shearing turbulence created by this profile of angular rotation. So without going inside our theory, all these hypotheses are sustained by the theory developed by Sands and then published with Charbonnier and so on, that the basement of the evolution theory, so the basement of the standard model, is that the rotation law is shell law, so it's a rotation law depending on the radius of the star, and this, to sustain the fact that the rotation law is shell law, you need a basic hypothesis, which is here, which assumes that you have a pre-existing anisotropic tolerance. So, under that assumption, people said, okay, now in the standard...
Sorry, what is DH?
Sorry?
What is DH?
D horizontal, D diffusion coefficient. So, just I was starting to answer to your question.
Yeah.
So, people had the standard model with micro-diffusion process, with in fact, their purpose was to add diffusion processes inside these models. And for example, Michaud had did microscopic diffusions, and it worked very well to restitute the HG, MN, and MFM phenomenon. Also, Michaud published with Charbonnier, they included the meridional circulation, and they were able to explain the release of HMN and the MFM phenomenon, which is so the appearance of some abundance at the surface of the star under a critical, particular equatorial velocity. So I summarize that. I don't go too much in detail. And now Zahn developed a theory to introduce turbulent diffusion, so macroscopic transport, and he assumed the separation between small and large scale. And from meridional circulation, he calculates a diffusion coefficient here, taking into account the azimuthal component. So exactly, yes, azimuthal components, if you want, of meridional circulation, and another coefficient more devoted to small scales, coming directly from the dimensional analysis, and we recognize what it is made in a way for when we study the number of theory. So everything was perfect, but when they tried to test the evolutionary model, standard model with turbulent transport, they found that they couldn't separate the two scales simply because they found that the two coefficients stayed always of the same order. So Zahn concluded, and recently did it. Suzanne Talon has published a review last year where she speaks about this. That it wasn't consistent to assume from the beginning that small scale and large scale of turbulence could be separated, and that a turbulent coefficient could be calculated separating the two scales. So from 1996, immediately, Michaud and Vincent at University of Montreal and Minibouzy, who works at Saclay, Lord de Maurizier in France, they tried to demonstrate that it wasn't consistent, and they did 2D simulation. They took inspiration from geophysics, in which the flow is a synthetic flow taking into account all scales of turbulence. And they fixed a spectrum which is the sum between a Kolmogorov component and a Kreisland component. Kreisland component, so K minus 3, with varying coefficients. And so by increasing this coefficient before the Kreisland components, they were able to create a strong horizontal anisotropic turbulence. So the vertical scale didn't change, as I said, because it was fixed by the Kolmogorov components, but they were able to increase the anisotropy of turbulence in the horizontal direction. To measure this anisotropies, they have defined this quantity, and also what is interesting for me is that what's important for me is they did the experiment, the simulation in 3D. So they had a big slides of fluid.
Sorry, what do you mean by Kreitmann component?
Sorry?
What do you mean by Kreitmann component?
Kreitmann?
Yes.
It's 2D turbulence.
Okay.
K-3. And it's
Oh, so you actually have a superposition of...
Yes, it's a sum.
But still, the flow field is not actually a solution of the Navier-Stokes equation. It's somehow artificial, right?
Yes, that's the first step. And the purpose of my PhD was to resolve Navier-Stokes equations.
Yeah.
It's the reason why I say it's important for me, because just to finish on this part, so they defined a vertical turbulent diffusion coefficient. And in fact, what they do, they put just a tracer, massive scala, in the flow with the initial Gaussian profile. And
what is the time correlation?
Time correlation between what and what?
This is the time-dependent flow.
No, it's not a time-dependent flow. You create a flow with a shearing. So the spectrum is fixed. So we create what is important in the study is to vary, to study the influence of the increasing anisotropy of the flow.
But how can you have diffusion of something that's not
That's okay.
I'm not
That's
finished.
a different kind of diffusion then.
You have just the equation of for the
It's
passive
ballistic,
scala.
I think.
That's
Is it always ballistic? That's probably true.
You can have a stationary flow, but it still could be random, of course. What
Yes,
she probably means is just the spectrum is stationary,
Yes.
but the flow itself will be random.
Yes.
random in what way? It's random in
Especially.
space, of course. You are saying it's stochastic Gaussian.
Yes.
Right.
But
time
what about
also.
in time?
It will be random.
It's
in
constant
time.
in time.
Sorry?
It's constant in time. Right?
It's constant in time or completely random in time?
The flow, the flow doesn't evolve with time. The flow is is calculated. You fix the flow. You have the velocity field calculated by this.
So is
The
that
flow. You have just the equation for the passive scalar. So in the
Okay,
equation, you see, you calculate the evolution of time of the diffusion of a passive scalar in the structure.
so is that Lagrangian chaos then?
Yes, yes, exactly. That's basically Lagrangian case.
I mean, if you have a static flow, then the only way to have diffusion is if the trajectories are chaotic.
See, your
Or
velocity
if you
field
consider
is,
short time scale. If you
Yeah,
consider
then
short
it is just as you're saying, ballistic, but it's
see, your velocity
You see,
field is
the
random
purpose
space.
of this study wasn't to do a realistic flow. The purpose
That's
was
okay.
to prove that it was inconsistent to separate large scale and small scale. Because what they saw is when so it's right that the diffusion of so they have not too much focus on the time needed, for example, for the scalar to diffuse inside this flow. They just try to see, what I remember, they try to be consistent with the time scale on which they are doing they did the experiments, that they were consistent about this. But on this time scale, when they calculate the vertical diffusion, so with say is a tracer in fact, depending on the anisotropy on the same time scale for the tracer, they found that the mixed length model, in fact, what I call the mixed length model is a way that the DH definition, the way that the DH is calculated. The mixed length model overestimates the vertical transport, in fact. The theories that then used the dimensional analysis, they concluded give vertical turbulent diffusion, a vertical turbulent diffusion which was too stronger. So when you increase the anisotropy, it's more and more true because you are under 1. When I equal 1, we are in the perfect case where it's completely isotropic. And when you increase the anisotropy of the flow, what they saw is that in fact the vortices were more and more flattened, and the transport by I would say isotropic turbulence could be much more important, much more determining the vertical diffusion than release anisotropic turbulence. So this involved the fact that possibly normally we thought that the turbulence involved by meridional circulation would be in charge of the vertical diffusion, and it's not necessarily true. We have to solve the complete problem of turbulence with also scale to be able to really figure what could happen.
When you say it's fully isotropic, then you basically mean that you have no Kreitmann component. It's all Kolmogorov.
Yes, when you fully isotropic, yes, this is 0. You are just, you see, and here you have 1, A equals 1. So dt is about this. It's here.
So then your advecting field is just a stochastic Gaussian field
Yes.
which has a spectrum of minus 5/3.
In a 5/3.
5/3, that's the Kolmogorov number, minus 5/3.
Yes, yes, 5/3. Yes. In this case, in the case I equal 1.
But is it a power law scaling all the way, or do you have a cutoff?
No, it's it's not a physics. It's not physics. We are demonstrating that it wasn't consistent, and my part was to do something physics. Okay.
By the way, in the previous part, the correlation links, the horizontal and vertical correlation links, how big?
I don't know, because I've not been go too much through this.
Yeah. Okay.
Okay.
Tell me, yeah.
If you have, you want to have information, the paper was published in '96.
Yeah.
So in fact, you wouldn't have so much compared to this, but it was really, the purpose was really to give some support to what people found when they try to test the diffusion coefficient in the standard model. And so, and in the same time, what I wanted to say is, what it was tricking, they found almost the same results if they did a simulation in 2D or in 3D. So I have shown in 3D, but they didn't find lots of differences. So what he has proposed to me, and I did my PhD between University of Montreal and Toulouse, and it was to generate by solving Navier-Stokes equations a flow with shearing layers. And the way we did it, so in fact it's always related in this case with the sun, in the sense that we are in the tachocline, the thickness of the tachocline is very small, so because we are quite far from the center, we can assume that we have the plane approximation, and this would be a small part of the tachocline with shearing. So to create this shearing, we have assumed this profile initially. So we start with no velocity, and with a forcing, we had to the Navier-Stokes equation. We create a flow with shearing layers. And with this forcing, we could control the number of shearing layers. So to prevent and to be able a study on quite a long time, so we fixed about 7 shearing layers. 7 shearing layers.
Why would you want several shearing layers?
Because the problem when at the beginning, when the stratification, because we are at the top of the radius, so we are stratified. If because we study the evolution of the anisotropy with the stratification, if you are not too much stratified, very fast the tracer reach the boundary. And our boundaries are fixed by the architecture of the code. It's risky. And we had lots of strong critique about the fact that our boundaries could false the results. So the only way was not to reach the boundary, to do the study before reaching the boundary. And the way to do it was to increase the number of shearing layers. If you have just 2 shearing layers, you have fastly a profile like this. So if you put a Gaussian on it, very fastly it diffuses to the boundary. And normally, what we would like to do is to do. I would like to do the same simulation, but with completely periodic boundary condition to prevent this problem of almost wall boundary. So this recipe is not wall, but you are obliged to have, for example, for the VZ 0 here, and for the temperature it's fixed on the top and the bottom, and perturbation is also. It's a little bit constraining only for the physics of the problem. And in a star, you have no boundary. That's always the same problem. People are doing studies about the development, for example, of Ekman layers, and they assume boundaries, and it's really criticized because there is no walls in the stars. So, and I did my simulation in 2D. with the same code as Alain Vincent is a code of the code coming from the Goddard Space Flight Center. And I have added Lagrangian particle tracking. I have used the Hermite polynomial interpolation with the Hermite polynomial. So the boundary conditions, as I said, are periodic in this direction, and so free slip, non-periodic in the vertical. And our numerical resolution was this one, 256. So it's the reason why I would like to have a minimum, to do 3D simulation with a minimum of the same resolutions. Here you have the effective value of the parameters of our simulation. The Richardson number varies and stays under 0.25, which is the Kelvin-Morse criteria. Our effective Reynolds number is around this value. Here you have the Peclet of the temperature, the Peclet of the tracer, which must be high to favorite the turbulent diffusion instead of the atomic one. And the Planck number is very small because we suggest that in a radiative SAR with a high conductivity, the Planck must be around 10 minus 6, 10 minus 4, and the Schmidt of the tracer is correspond to the Planck. We don't run for the tracer because it was, so it's an order of unity.
With this Richardson number, that means that the shear is unstable to the Helmholtz equivalency.
Yes, we are unstable. The purpose is to create, starting from velocity field equal to 0 to see the development of the Kelvin-Morse instability and the turbulence and the shearing, turbulence and shearing layers. So, I will show on the next slide the vorticity and the tensor. So, I don't go too much in the kitchen, but what we do, so when we did the simulation to obtain this shear turbulent flow, we had to define a time-space area where we could consider that the flow was quasi-stationary, in the sense that the anisotropy defined here didn't vary too much and respect some error bars we defined after maneuvers. And what we selected to present for the PhD, it's a set of 10 simulations with the average anisotropy calculated about this time box. So time is between 6 and something like 80, so it's a dimension. And the box is defined by the size of expansion of the tracer. So for each case, we calculate each time the size of expansion of the tracer, and it defines our time-space box. And what we observe is that for the 5 first one, our simulations are quite similar to the simulations of Vincent et al. In particular, the product SZ, so also we have defined a vertical length scale and a velocity length scale. We have inspired from the classical definition, we have adapted our definition to this space-time box. So we find that this product stays constant, and it is what mainly the flow of Vincent et al. Imposed, because the Kolmogorov spectrum was fixed and just we varied the coefficient of the equation one. But what we found, so normally Vincent Centauri are able to do this for up to 100, anisotropy to 100. What we found, we stopped around 10, and above 10, anisotropy above 10, at high stratification, this product decreased, and we found a stop, the diffusion coefficient also the variation of the diffusion coefficient asymptotically tends to 0. So the diffusion coefficient tends to keep the same value as a stop of the vertical diffusion at high stratification. And this result wasn't predicted or even seen by the simulation of the Sci-Fi. So, to finish above on the Sci-Fi, so this is a definition of our turbulent diffusion coefficient and the definition of our Lagrangian diffusion coefficient calculated with a particle tracking. So we have put 280,000 particles. Here you have the profile of the tracer, so for the lower stratification. So lower stratification is the lower anisotropy, the highest anisotropy. And this is the initial profile, and we see that it's the vertical diffusion is reduced when you increase stratification, and when we plot these two coefficients divided in the same way as this cycle divided by the product LZ to Z, we see that at low stratification for A above 3, we seem to be quite close by what was predicted by the law of Nordita. But above 10, we have a straight increase, and this straight increase is linked to the fact that the product LZ decreased, but in fact the two coefficients stay quite constant. It's not constant, but they stay on average quite constant. There is a stop of vertical diffusion. The difference between two is when you have a Lagrangian particles, you have just advection of particles. So the difference is linked to an appearance of the diffusion from the normal atomic diffusion process included in this.
In the plot for high stratification, this Gaussian doesn't seem to spread at all.
Yes.
But when you somehow normalize with some dimensionlessly, it increases the diffusion coefficient in the high stratification case, right?
No.
So I'm confused.
No, yes, because the product in this range, the product LZBZ is more constant. It decreased too. So something constant divided by something which decreased, we see an increase. You see, this value doesn't change a lot anymore,
Right.
and this decrease.
So why it decreases LZBZ?
Simply because the vertical diffusion is stopped. So the vertical, it's not like in Benzytal. Our LZBZ can change. And because the vertical diffusion is stopped, and is stopped mainly, it stopped thanks to the shape of the turbulence level. It's more, and the vortices are more and more elongated. So the particle has not time to go very high and to go back. So we have a kind of kill turbulence appearing. You see a swift turbulence swift. There is a name for this.